Now in this lecture I will answer two questions. The first question, we find out the radius of this circle, and the second question, we find out the area of this circle using two different methods. We'll start with the first question. In the domain we have a circle and the right triangle ABC. Point O is the center of this circle. Side AB of triangle ABC is equal to 13 units in its length and to 3 units in its length. This is side line segment AD. This is equals to 3 units in its length. This is line segment DC. This is equals to 1 unit in its length. This is angle ABC. That is the right angle. Again, our test is to find out the radius of this circle. So, if we focus on the common start point C, on the common start point C we have tangent CE. It is tangent to this circle at point E, and we have also secant CA that cuts the circle at point D and at point A. So here we can implement all 25. So repeat quickly on all 25. According to all 25, if from a common external point, this is the common external point P, we draw a tangent PA that is tangent to this circle at point A, and we will also draw the secant PC that cuts the circle at 2 points B and C. So in this drawing, the following equation is true: that PA square equals to PB times PC. Again, PB square equals to PB times PC. So we can actually implement all 25 in our drawing. In our drawing, so I already mentioned before, if we focus on this common external point C, on this common external point C, we have tangent CE, that is tangent to this circle at point E, and we have secant CA that cuts the circle at 2 points D and A. So all the requirements for 25 are satisfied, and therefore we can implement all 25 in our drawing if we focus on the common start point C. So I write it down. So on the common start point C, we implement all 25. According to all 25, CE square equals to CD times CA. Repeat again, according to all 25, if we focus on the common start point C, the following equation is true: that CE square equals to CD times CA. C is the missing side, so whatever it is, it is CE square CE square equals to CD. CD is 1 times CA. CA in total is 1 plus 3, that is 4. So in total, according to equation 4, according to all 25, we found out that CE square equals to 1 times 4. 1 times 4 is 4. So CE square equals to 4 according to all 25. Here we take the root out of this equation, and we get that CE equals to the square root of 4, that is 2. So the length of tangent CE is 2 units. This is tangent CE, it is equals to 2 units in its length. In the next step, we will implement the Pythagoras theorem on the right big triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I will copy the right triangle ABC in a new page and we will implement on it the Pythagoras theorem. The hypotenuse AC equals to 3 plus 1, that is 4. AB equals to 3, and BC is the missing side. Here by PT is the variation for Pythagoras theorem. Okay, this is the right triangle. This is the right triangle ABC, this is the corresponding drawing. This right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I write it down. AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so notice it is. So in total, we actually found out that 16 equals to 9 plus BC squared. Here we subtract 9 from this equation, and we get that BC squared equals to 16 minus 9 is 7. So BC squared equals to 7. Here we take a root out of this equation, and finally we get that the missing side BC is equal to the square root of 7 units in its length. So actually, this is the missing side BC, that equals to the square root of 7 units in its length. So write it down in the drawing that BC equals to 7 units, to the square root of 7 units in its length. What is the length of this missing line segment? Line segment BE. For the drawing, it is very easy to see that BE equals to BC minus EC. Again, BC minus EC equals to BE. So write it down. BE equals to BC minus AC. So BE equals to BC. BC is square root of 7 units in its length. Minus EC. EC equals to 2. So in total we found out that B equals to the square root of 7 minus 2 units in its length. This is 97 BC. Is equals to the square root of 7 minus 2 units in its length. In the next step, we will join points O and E together by straight line. Point O is the center of the circle. Point E is the point of tendency of tangent BC with this circle. Again, point O is the center of this circle. Point E is the point of the circle itself. Therefore, OE is the radius of this circle. We will define the radius of this circle as R. So OE equals to R. This is the radius of the circle that is equals to R. The radius OE that is equals to R. The radius OE is 1 to point E, that is the point of tendency of tangent BC with this circle. Whenever you have radius that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from this point O, that is the center of this circle, we will draw perpendicular on side AB. Here from point O, we will draw perpendicular on side AB. So if this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O inside AB. This point is point F. By doing this construction, we created quadrilateral FOEB. Inside quadrilateral FOEB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees. According to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So in quadrilateral FOEB, we have 4 right angles, and therefore, according to rule 5, quadrilateral FOEB is a rectangle. So write it down. Quadrilateral FOBE is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle FOEB, side BE must be equal to the opposite side FO, but BE is square root of 7 minus 2, therefore the opposite side FO must be equal to square root of 7 minus 2 units in its length. Likewise, according to the same rule, in the same rectangle FOEB, side OE must be equal to the opposite side FB, but OE equals to R, it is the radius of the circle, therefore the opposite side FB must be also equal to R. FB equals to R. FB equals to R. what is the length of this missing 97 AF? From the drawing, it is very easy to see that AF equals to AB minus FB. Again, AF equals to AB minus FB. So it is known AF equals to AB minus FB. So AF in total equals to AB. AB equals to 3 units in its length, according to what is given as the question. Minus FB. FB equals to R. So in total we should know that the length of the missing 970 AF is equal to 3 minus R. This is 970 AF, that equals to 3 minus R units in its length. In the next step, we'll join points A and O together by a straight line. Point A and point O is the center of this circle. Point A is the point of the circle itself, therefore OA is the radius of this circle, that is equal to R according to our definition. In the next step, I'll copy the right green triangle AFO in a new page, and we will implement the Pythagoras theorem on this right green triangle AFO. Here by PT is the promotion for Pythagoras theorem. So actually, this is the right green triangle AF4 that according to the original drawing. In this right triangle AF4, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AF squared plus FO squared. So I write it down. AO squared, that is the square of the hypotenuse, equals to AF squared plus FO squared. AO equals to R, therefore AO squared is equal to R squared, and it is equal to AF squared. AF equals to 3 minus R, therefore AF squared equals to 3 minus R squared plus FO squared. FO equals to the square root of 7 minus 2, therefore FO squared in total equals to 0.417 units. So I check if I'm not wrong. FO squared equals to square root of 7 minus 2 squared is actually 0.417. So in total we found out that r squared equals to 3 minus r squared plus 0.417. So r squared equals to 3 minus r squared. 3 minus r squared equals to 3 squared, that is 9, plus r squared, minus 2 times 3 times r, that is minus 6r, plus 0.417. We have r squared on both sides of this equation. So r squared gets cancelled. After I cancel r squared, on this side of the equation we left with nothing, that is to say 0. While on the other side of this equation we have 9 plus 0.417, that is 9.417, minus 6r. Here we will add 6r to this equation, and we get that 6r equals to 9.417. Here we will divide this equation by 6. And we get that r equals to 9.417 over 6. .417 over 6 is 9.57. Yeah. 9.417 over 6 is equal to 9.57. 9.417 over 6 equals to 1.57 units. So if you found out that the radius of this circle, that is the radius that we are looking for in this question, is equal to 1.57 units in its length. So finish with the first question. In the next step I will present you the second question, and we solve the second question by using two different methods. In the second question, our task is to find out the area of this circle. In the moment we have a circle. This is line segment BC, that is equals to 6 units in its length. This is line segment, this is chord BA, that is equals to 13 units in its length. This is line segment CD, that is equals to 18 units in its length. This is angle ABC, that is a right angle. This is angle BCD, that is also a right angle. Again, our test is to find out the area of this circle. So first of all, those two angles are defined as one-sided interangles. The sum of those two angles is 90 degrees plus 90 degrees. It is equal to 180 degrees. And according to Rule 27, whenever you have two one-sided interangles, the sum of those two angles is 180 degrees, then they must be located between parallel lines. That is to say, side BA is parallel to side CD. So I pitch quickly on Rule 27. According to Rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. In the drawing we have line A, this is line A, this is line B. Line C, this is line C that cuts line A and line B here at those 2 points. Those 2 angles are defined as one-sided interangles. So if the sum of those 2 angles alpha and beta that are defined as one-sided interangles, if the sum of those 2 one-sided interangles is equal to 180 degrees, then they are located between parallel lines. That is to say, line A is parallel to line B. Again, if alpha plus beta is equal to 180 degrees, then line A is parallel to line B. So as I mentioned before, we can implement rule 27 in our drawing. Why? Because in our drawing, the sum of those 2 one-sided interangles is equal to 180 degrees, and therefore, according to rule 27, those 2 angles are located between parallel lines. That is to say, line BA is parallel to line CD. So in the drawing, we found out that line segment BA, or chord BA, is parallel to chord CD according to rule 27. BA is parallel to CD according to rule 27. In the next step, we will define the center of this circle, this point O, and we will do a construction, that is to say from the center of this circle, that is to say from point O, we will do perpendicular on CD. Again, from point O, we will do perpendicular on CD. So actually, this angle equals to 90 degrees in its size, and this angle also equals to 90 degrees in its size according to our construction. We will define the touching point of the perpendicular from point O and side CD, this point is point M. In the next step, we will extend the perpendicular DM, we will extend the perpendicular OM by side line until it touches chord BA. Again, we will extend the perpendicular OM by side line until it touches chord BA. And we will define the touching point of the extended perpendicular OM with chord BA. This point is point N. And because of the fact that according to rule 27, line segment CD is parallel to line segment BA, it means that the perpendicular OM, the perpendicular that we drew from point O, that is the center of this circle, must be also perpendicular to chord BA. Why? Because they are parallel to each other. So this angle equals to 90 degrees. And this angle also equals to 90 degrees because of the fact that line segment CD is parallel to chord BA. So if OM is perpendicular to CD, then the extended OM must be also parallel. The extended perpendicular OM must be also perpendicular to BA because they are parallel to each other. Okay, so here we can implement rule 19. Repeat quickly on rule 19. According to rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. In the moment we have a circle, point towards the center of the circle. OM is perpendicular to chord AB. Again, OM is perpendicular to chord AB. That is to say, this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB as M, and according to this rule 19, perpendicular OM bisects the chord AB. If perpendicular OM bisects chord AB, it means that AM equals to MB. AM equals to MB according to this rule, rule 19. So we can definitely implement rule 19 in our drawing. Well, because in our drawing, from the center of this circle, that is to say from point O, we do perpendicular ON or chord BA. Again, from point O, that is the center of this circle, we do perpendicular ON or chord BA. And according to rule 19, perpendicular ON bisects chord BA. If perpendicular ON bisects chord BA, and BA in total equals to 13, it means that the first half BN must be equal to 13 over 2, that is 6.5. And the second half of BA, that is NA, must be also equal to 6.5 units in its length, according to rule 19. Okay, so by doing the construction here, we get the upper quadrangle BCMN. Inside this quadrangle BCMN, we have 1, 2, 3 rectangles. Actually, we can also say that ON as a perpendicular, it is absolutely a straight line. So if we focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line ON at point M? We have this angle that is the right angle, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. Another way to find out that the missing angle here equals to 90 degrees in its size is as follows. If we focus on quadrangle BCMN, in quadrangle BCMN, we have 1, 2, 3 rectangles. The sum of 3 rectangles is 270 degrees. So 270 degrees plus the size of this 4 pieces angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore this 4 pieces angle must be equal to 90 degrees in its size. So inside quadrangle BCMN we have 4 rectangles, and according to rule 5, and quadrangle that has 4 rectangles must be it is a rectangle if not a square. So you relate to quadrangle BCMN as a rectangle because it has 4 right angles. So it's known the upper quadrangle BCMN is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CM. But BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. In the next step, we will do another construction, that is to say, from this point A, we will draw perpendicular on line segment CD. Again, from point A, we will draw perpendicular on line segment CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point A and line segment CD. This point is point L. By doing this construction, we created the lower quadrangle NMLA. Inside this lower quadrangle NMLA, we have 1, 2, and 2 rectangles, but this angle is equal to 90 degrees according to rule 3. Why? Because if you focus on the upper side of the straight line, if we focus on the lower side of the straight line NO at point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Again, rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line NO at point M? We have this angle that is the right angle, plus this is an angle. In total, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So inside the lower quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral MNLA we have 4 right angles, and therefore according to rule 5, quadrilateral MNLA is a left angle. So it's known. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle MNLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing line segment LD? From the drawing, it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So write it down. LD equals to CD minus CL. So in total, LD, this missing line segment LD is equal to CD. CD equals to 18 units in its length, according to what is given as the question. Minus CL. CL in total equals to 6.5 plus 6.5, that is 13. CL equals to 13, so in total LD equals to 18 minus 13, that is 5. So if you found out that the missing line segment LD is equal to 5 units in its length. So it is known, this is the missing line segment LD, that is equal to 5 units in its length. In the next step, we will extend line segment DC by straight line until it touches the circle. And we will define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we created chord TD. This is chord TD. And from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. Again, from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. And therefore, according to rule 19, perpendicular OM, that is run from the center of this circle, that is to say from point O, perpendicular OM bisects chord TD. Again, perpendicular OM bisects chord TD. That is to say, TM equals to MD according to rule 19. So I did not know if you found out that according to rule 19, TM equals to MD. But MD in total equals to 6.5 plus 5. Again, MD in total equals to 6.5 plus 5. 6.5 plus 5 is 11.5. MD equals to 11.5. And from this equation, TD equals to MD equals to 11.5. We derive that TM is also equal to 11.5 units in its length. This is line segment TM, that equals to 11.5 units in its length. So from one side, TM equals to 11.5 units in its length. But from the other side, TM also equals to TC plus CM. Again, TM equals to TC plus CM. On the other side, TM equals to TC plus CM. So 11.5 equals to TM, and TM equals to TC plus CM. TC is the missing side, so we leave it as it is. So it is equals to TC plus CM. CM equals to 6.5. And from this long equation, we will derive that 11.5 equals to TC plus 6.5. 11.5 equals to TC plus 6.5. Here we will subtract 6.5 from this equation, and we get that the missing side TC is equal to 11.5 minus 6.5 is 5. So the missing line segment TC is equal to 5 units in its length. This is the missing line segment TC, that is equal to 5 units in its length. In the next step, we will extend line segment BC by a straight line until it touches the circle. And we define the touching point of the extended line segment BC with this circle. This point is point Q. In the next step, we will join points Q and A together by a straight line. So by doing this construction, we created here peripheral angle ABQ. This is peripheral angle ABQ. The size of peripheral angle ABQ is 90 degrees. And peripheral angle ABQ subtend on chord QA. Again, peripheral angle ABQ subtend on chord QA. So here we can implement all 5 in our drawing. But before that, we will implement all 15 in our drawing. We have here, this is code TD that intersects with code BQ at point C. Again, code TD intersects with code BQ at point C. So we can implement all 15. According to rule 15, if code AB intersects with code CD at point O, then the following equation is true, that AO times OB equals to CO times OD. In the drawing we have a circle, this is code AB that intersects with code CD at point O. Again, code AB intersects with code CD at point O. So in this drawing, the following equation is true, that AO times OB equals to CO times OD. So we can implement Rule 15 in our drawing. So as I mentioned before, chord TD intersects with chord BQ at point C. So all the requirements of Rule 15 are satisfied, and therefore we can implement here Rule 15. So write it down. In our original drawing, chord TD intersects with chord BQ at point C. Repeat again. Now original drawing, we have chord TD that intersects with chord BQ at point C. So all the requirements of Rule 15 are satisfied, and therefore we can implement Rule 15. According to Rule 15, the following equation is true, that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. So write it down. TC times CD equals to BC times CQ. Repeat again, according to Rule 15, the following equation is true. That TC times CD equals to BC times CQ. TC is 5 times CD. CD equals to 18 units in itself, according to what is given as a question. Again, TD is 5, CD is 18, and it is equals to BC times CQ. BC equals to 6 units in itself, according to what is given as the question, times CQ. CQ is the missing size of limited city. So in total, according to Rule 15, we have found out that 5 times 18 equals to 6 times CQ. Here we will divide this equation by 6, and we get that 18 over 6 is 3, and 3 times 5 is 15. So in total, we found out that the missing 97 CQ is equal to 15 units in its length. This is the missing 9 segment CQ that is equals to 15 units in its length. So, by joining points A and Q together by sunline, you can deduce peripheral angle ABQ. Peripheral angle ABQ is equal to 90 degrees in its size, according to what is given in the question. And peripheral angle ABQ subtend on chord QA. Again, peripheral angle ABQ subtend on chord TA. So can implement here Rule 5. Repeat quickly on Rule 5. According to Rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing we have a circle. This is peripheral angle MAN that is equal to 90 degrees in its size. And therefore, according to this Rule 5, peripheral angle MAN, that is the right angle, must subtend on the diameter of the circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of the circle. So according to this Rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. So we can definitely implement Rule 5 in our drawing. Why? Because in our drawing, this is peripheral angle ABQ that is equal to 90 degrees in size. And therefore, according to rule 5, peripheral angle ABQ, that is the right angle, must subtend on the diameter of the circle. Peripheral angle ABQ subtend on chord AQ, and therefore, according to rule 5, chord AQ must be the diameter of the circle. So write it down. Chord AQ is the diameter of the circle according to rule 5. The diameter of any circle is twice as long as the radius. So if you define the radius of this circle as r, then the diameter AQ must be equal to 2r in its length. In the next step, I'll copy the right triangle ABQ in a new page, and we will implement the Pythagoras theorem on this big triangle ABQ. Side AB equals to 13 units in its length. Side BQ in total equals to 6 plus 15, that is 21. And the diameter AQ is the hypotenuse AQ is also the diameter of the circle. Therefore, it is equals to 2r. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle ABQ that is coming from the original drawing. In this right triangle ABQ, according to the Pythagoras theorem, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. Again, QA squared equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, is equal to QB squared plus BA squared. QA equals to 2r, it is the diameter of the circle. Therefore, QA squared is 4r squared, and it is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441 plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, we actually found out that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So in total, we found out that 4r squared equals to 610. Here we will divide this equation by 4, and finally we get that r squared equals to 610 over 4. 610 over 4 is 152.5. R squared equals to 152.5. Our task is to find out the area of the circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of the circle squared times the radius of our circle squared. The radius of our circle squared is r squared. So the area of our circle must be equal to pi r squared. So it is pi times r squared, and r squared is 152.5. So in total, we found out that the area that we're looking for this question, that is the area of the circle, equals to either pi times 152.5 square units in its size, or in terms of numbers, this expression is equal to 479.09 square units in its size. Repeat again, if you found out that the area that we are looking for in this question, that is the area of the circle, is equal to either 152.5 pi square units in its size. In terms of numbers, the area of the circle is equal to 479.09 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use the things that we already found out in the first method. Actually, in the first method, we have already found out that the line segment CQ is equal to 15 units in its length. This is line segment TC, this is equal to 5 units in its length. So we use this data in the second method. So here we can implement rule 26. Repeat quickly rule 26 according to rule 26. First of all, rule 26 is true in any circle. So in any circle, if two chords, that is to say A, B and C, D, intersect with each other, if two chords A, B and C, D intersect with each other at a right angle, we have here chord AB intersects with chord CD at a right angle. This angle equals to 90 degrees. They intersect with each other and they create 90 degrees at the point of the intersection, that is point O. So if two chords intersect with each other at a right angle, then the following equation is true. That AO square plus OB square plus CO square plus OD square equals to 4R square. R is the radius of this circle. Again, if chord AB intersects with chord CD at 90 degrees, then the following equation is true, that AO square plus OB square plus CO square plus OD square equals to 4R square. We can definitely implement rule 26 in our drawing. One good in our drawing, we have chord, this is chord TD that intersects with chord BQ at 90 degrees. This angle equals to 90 degrees. So all the requirements, this angle equals to 90 degrees. Again, chord QB intersects with chord TD at 90 degrees. This angle equals to 90 degrees. They create between them 90 degrees at the point of the intersection, that is point C. This angle equals to 90 degrees. So all the requirements of rule 26 are satisfied, and then one can implement here rule 26. So I write it down. We have chord TD intersects with chord BQ at 90 degrees, and the intersection point occurs at point C. Repeat again. In our original drawing, chord TD intersects with chord BQ at 90 degrees, and the intersection point occurs at point C. So all the requirements of Rule 26 are satisfied, and therefore can implement Rule 26 in our drawing. According to Rule 26, the following equation is true. Let TC square plus CD square plus BC square plus CQ square equals to 4R square. Again, TC square plus CD square plus BC square plus CQ square equals to 4R square. So I do now, according to Rule 26, TD square, TC square, this is TC square plus CD square plus BC square plus CQ square, total is equal to 4R square. Again, according to Rule 26, the following equation is true. The TC square plus CD square plus BC square plus CQ square equals to 4R square. This equation is the implementation of Rule 26 in our drawing. TC is 5, therefore TC square is 5 squared, that is 25. Plus CD square. CD is 18, therefore CD square is 18 squared, that is 324. Plus BC square. BC is 6, therefore BC square is 6 squared, that is 36. Plus CQ square. CQ is 15, therefore CQ square is 15 squared, that is 225. And it is equals to 4R square. So in total, we should find out that (25 plus 324 plus 36 plus 225 equals to 4R square. 25 plus 225 is 250, and 324 plus 36 is 360. So 250 plus 360 equals to 4R square. 250 plus 360 is 610, so 610 equals to 4R square. Here we divide this equation by 4, and get that R square equals to 610 over 4 is 152.5. Our task is to find out the area of this circle. So actually we know that the area of any circle equals to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So the area of the circle is pi R squared. So it is pi, and R squared is 152.5. So we solve R squared by 152.5. So in total, we should find out the area of this circle, that is the area that we are looking for. In this question, according to the second method, is equal to either 152.5 pi square units in size, or in terms of numbers, it is equal to 479.09 square units in its size. So, in both methods, we arrive to the same result. So in the next step, we start the lecture. We start with the first question, of course. Our task in the first question is to find out the radius of this circle. So in the drawing we have a circle. This is the right angle ABC. This is angle ABC. This is right angle. This is side AB. This is equals to 4 units in itself. This is line 70 AD. This is also equals to 4 units in itself. This is line 70 C. This is equals to 1 unit in itself. Again, our task is to find out the radius of this circle. So first of all, we implemented all 25 on this common standpoint, point C. We have here tangent CE that is tangent to this circle at point E, and we have also secant CA that cuts the circle to points D and A. Therefore, we can implement here all 25. According to all 25, CE squared equals to CD times CA. Again, CE squared equals to CD times CA. Again, if we focus on the common standpoint point C, according to all 25, CE squared equals to CD times CA. CE is the missing side, so we limit to CTs, and it is equals to CD. CD is 1, and CA in total equals to 1 plus 3, that is 4. So in total, CD is 1, CA is 4, so in total CE squared equals to 1 times 4, that is 4. So CE squared equals to 4. Here we took a root of this equation and found out that CE, the length of tangent CE is equals to the square root of 4, that is 2. So this is tangent CE is equals to 2 units in its length. In the next step, we implemented the Pythagoras theorem on this right angle triangle ABC. According to the Pythagoras theorem, in any right angle, the square of the hypotenuse is equal to the sum of the squares of the perpendiculars. So actually, this is the right angle ABC that is coming from the original domain. This right angle ABC, AC squared equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and this is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so we limit to 16. So in total, we found out that 16 equals to 9 plus BC squared. Here, subtract the 9 from this equation, and we found out that BC squared equals to 16 minus 9 is 7. So BC squared equals to 7. Here, we took out of this equation, and we found out that the missing side BC is equals to the square root of 7 units in its length. This is the missing side BC, this is equals to square root of 7 units in its length. What is the length of EC? From the drawings, it's very easy to see that EC equals to BC minus EC equals to BC minus PE. Again, actually, we want to find out the length of the missing line segment BE, and BE equals to BC minus EC. Again, BE equals to BC minus EC. Again, B equals to BC minus EC. So B equals to BC, that is square root of 7, minus EC, that is 2. So in total, B equals to the square root of 7 minus 4 units in its length. In the next step, we join points O and A together by a straight line. Point O is the center of this circle, point A is the point of the circle itself, therefore OE is the radius of the circle, that is equals to R according to our definition. The radius of OE, that is equal to R, the radius of OE is drawn to point E, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. In the next step, we did the construction, that is to say from point O, that is the center of this circle, we do perpendicular on AB. Again, from point O, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the tangent point of the perpendicular from point O and AB. This point is point F. When doing this construction, we can do quadrilateral OFBE. Besides quadrilateral OFBE, we have 1, 2, 3 angles. The sum of 3 angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral OFBE we have 4 angles, and therefore according to rule 5, quadrilateral OFBE is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So rectangle OFBE, side OE must be equal to the opposite side FB. but OE is R, therefore the opposite side EB must be also equal to R. Likewise, according to the sum rule, in the sum rectangle OFBE, side BE must be equal to the opposite side FO, but BE is square root of 7 minus 2, therefore the opposite side FO must be also equal to square root of 7 minus 2 units in its length. In the next step, we join point O and A together by set time. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle, is equal to R, according to our definition. In the next step, I copied the right triangle AF4 in a new page and we implemented the Pythagoras theorem on this right triangle AF4. But what is the length of AF? AF equals to AB minus FB. Again, AF equals to AB minus FB. So AF equals to AB, that is 3, minus FB, that is R. So in total, AF equals to 3 minus R. AF4 equals to the square root of 7 minus 2, and AO, the hypotenuse AO is equal to R. It is also the radius of the circle. So actually, this is the right triangle AF4, that is according to the Newton drawing. This right triangle AF4, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AF squared plus F4 squared. AO is R, therefore AO squared is R squared, and it is equal to AF squared. AF is 3 minus R, therefore AF squared is 3 minus R squared, plus F4 squared. F4 is square root of 7 minus 2, therefore F4 squared is square root of 7 minus 2 squared, that is 0.417. So in total, we found out that R squared equals to 3 minus R squared plus 0.417. So R squared equals to 3 minus R squared. Here we open the bracket and we found out that actually that 3 minus R squared equals to 3 squared, that is 9, plus R squared, minus 2 times 3 times R, that is minus 6R, plus 0.417. So here we have R squared on both sides of the equation, so R squared gets cancelled. So in this side of the equation we have nothing, 0. On the other side of the equation we have 9 plus 0.47, 9 plus 0.417 is 9.417, minus 6R. So in total we found out that 0 equals to 9.417 minus 6R. Here we added 6R to this equation, and finally found out actually that 6R equals to 9.417. Here we divided this equation by 6 and found out that the radius of this circle, that is the radius that we are looking for this question, is equal to 1.57 units in its length. So finish with the first question. In the next step I presented to the second question, and we solve the second question in 2 different methods. Our task in the second question is to find out the area of this circle. In the drawing we have a circle. This is line 7BC, that is equal to 6 units in its length. This is line 7BA, that is equal to 13 units in its length. This is line 7CD, that is equal to 18 units in its length. This is angle ABC, that is right angle. This is angle BCD, that is also right angle. Again, our task is to find out the area of this circle. So first of all, those two angles are defined as one-sided triangles and are located between line BA and line CD. So because of the fact that the sum of those two one-sided triangles is equal to 180 degrees, they must be located between parallel lines. That is to say, line 7BA is parallel to line 7CD according to rule 27. Okay, here. BA is parallel to CD according to 27. In the next step, we define the center of this circle. This point is point O. From point O, we go perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O, and CD, this point is point M. In the next step, we extended the perpendicular OM by straight line until it touches port BA. We define the touching point of the extended perpendicular OM with chord BA. This point is point N. And because of the fact that perpendicular OM is perpendicular to line 7 CD, the extended perpendicular OM, that is ON, must be also perpendicular to chord BA. Why they are parallel to each other? So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the rule that I mentioned. Those two line segments are perpendicular to each other, therefore the perpendicular to CD must be also perpendicular to chord BA. Okay, so by doing this construction, we can deduce quadrilateral BCMN. But before that, if we focus on the lower side of the perpendicular ON, that is the straight line at point M, here the sum of the angles must be equal to 180 degrees and 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So the sum of the angles on the lower side of the straight line OM at point M must be equal to 180 degrees. So which angles we have at the lower side of the straight line OM at point M? We have this angle that is 90 degrees according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees, and therefore this missing angle must be equal to 90 degrees in its size. Likewise, if you focus on the upper side of the straight line ON at point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. So which angles we have at the upper side of the straight line ON at point M? We have this angle that is the right angle according to our construction, plus this missing angle. In total, the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. So those two angles are both right angles. So in quadrilateral BCMN, we have 2, 3 right angles. This angle equals to 90 degrees according to what is given as a question. Actually, in total, in quadrilateral CBNM, we have 1, 2, 3, 4 right angles. So all those angles are right angles. And therefore, quadrilateral BCMN is a right angle, because it says 4 right angles. But we also know that the opposite sides of a right angle are equal to each other. So a right angle BCMN, side CM must be equal to the opposite side BN. But BN equals to 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. Likewise, we actually did a construction from point A with one perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and CD. This point is point N. When doing this construction, we created the lower quadrilateral MN AL. Inside the lower quadrilateral MN AL, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So inside quadrilateral MNLA we have 4 right angles, and therefore according to rule 5, quadrilateral MNLA is a right angle. But we also know that the opposite sides of a right angle are equal to each other. So right angle NMLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this missing line segment LD? From the drawing it is very easy to see that LD in total equals to CD minus CL. Again, LD equals to CD minus CL. So LD equals to CD, that is 18 according to what is given in the question, minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total, LD equals to 18 minus 14, that is 5. This is the missing side LD, this is equals to 5 units in its length. In the next step, we did a construction. Actually, we extended line 7 DC by straight line until it touches the circle. We define the touching point of the extended line 7 DC with this circle. This point is point T. By doing this construction, we graded it chord TD. Chord TD, we have here the perpendicular OM towards chord TD. According to rule 19, the perpendicular OM that is drawn from the center of this angle, that is to say from point O, the perpendicular OM by set code TD. If OM by set code TD, it means that TM equals to MD. Again, according to rule 19, TM equals to MD. But MD equals to 6.5 plus 5, that is 11.5. MD equals to 11.5, and from this equation TM equals to MD equals to 11.5, we will derive that TM also equals to 11.5. This is 9 segments TM that equals to 11.5 units in its length. So from one side TM equals to 11.5, but from the other side TM equals to TC plus CM. Again, TM equals to TC plus CM. On the other side, TM equals to TC plus CM. So 11.5 equals to TM, and TM equals to TC plus CM. TC is the missing side, so we leave it as it is, plus CM. CM is 6.5. Again, CM is 6.5. So in total, TC plus CM is TC plus CM, and CM is 6.5. And from this long equation, we will derive that 11.5 equals to TC plus 6.5. 11.5 equals to TC plus 6.5. Here we subtracted 6.5 from this equation, and we found out that the missing side TC is equals to 11.5 minus 6.5 is 5. This is 97 TC, this equals to 5 units in its length. In the next step, we did the construction, that is to say, we extended 97 BC by straight line until it touches the circle. We define the touching point of the extended 97 BC with this circle. This point is point Q. So here we can implement rule 15 because we have code TD that intersects with code BQ at point C. Again, code TD intersects with code BQ at point C. Repeat again. Now, original drawing code TD intersects with code QB at point C. So we can implement all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, the following equation is true that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. And again, according to rule 15, TC times CD equals to BC times CQ. So TC is 5. CD is 18, and it is equals to BC 36 times CQ. So in total, we found out that 5 times 18 equals to 6 CQ. You will divide this equation by 6. 18 over 6 is 3, and 3 times 5 is 15. So this is the missing line segment CQ. This is equal to 15 units in its length. In the next step, we join point Q and A together by straight line. When doing this construction, you can do this is peripheral ABQ. This equals to 90 degrees in size according to what is given as the question. And the peripheral ABQ subset on code QA. Again, peripheral ABQ subset on code QA. And according to rule 5, any peripheral that is equal to 90 degrees in its size must subset on the diameter of the circle. So peripheral angle ABQ is equal to 90 degrees in its size, and therefore it must subset on the diameter of the circle. Peripheral ABQ subset on QA, on code QA, and therefore according to rule 5, code QA must be the diameter of the circle. If QA is the diameter, it's twice as long as the radius. So if the radius is R, then QA must be equal to 2R. In the next step, I call it the right triangle ABQ in the page, and we implemented the bottom one on this right triangle ABQ. PQ equals to 6 plus 15, that is 25. BA equals to 13, and QA is the diameter of the circle, that is 2R. So this is the right triangle ABQ that according to the original domain, according to the bottom one in this right triangle ABQ, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So QA is 2R, therefore QA squared is 2R squared, that is 4R squared, and that is equals to QB squared. QB is 21, therefore QB squared is 21 squared, that is 441, plus BA squared. BA is 15, therefore BA squared is 15 squared, that is 169. So in total, we found out that 4R squared equals to 441 plus 169. 441 plus 169 is 610. So 4r squared equals to 610. We divided this equation by 4 and found out that r squared equals to 610 over 4, that is 152.5. Our test is to find out the area of this circle. And here we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so in total the area of our circle must be equal to pi r squared, but r squared is 152.5, therefore we substitute r squared by 152.5, and we found out that the area of the circle is equal to pi times 152.5 square units in size, so in terms of numbers, the area of our circle must be equal to 479.09 square units in size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use with the fields that we already found out in the first method. We already found out that line 70Q equals to 15 units in its length, and line 70C equals to 5 units in its length. So here we implemented rule 26 in our drawing. Repeat on rule 26. According to rule 26, rule 26 is for any circle. So in any circle, if two chords A, B, and C, D intersect with each other at a right angle, and the intersection point occurs at point O, then the following equation is true. That AO squared plus BO squared plus CO squared plus DO squared equals to 4R squared. In the drawing we have a circle. This is called AB that intersects with called CD at 90 degrees. They create the intersection point O, 90 degrees between them. And therefore, in this drawing, the following equation is true. That AO squared plus OB squared plus CO squared plus OD squared equals to 4R squared. R is the radius of the circle. So we can implement rule 26 in our drawing. One put in our drawing, chord TD intersects with chord BQ at 90 degrees. This angle equals to 90 degrees according to what is given as a question. So all the requirements of rule 15 are satisfied, of rule 26 are satisfied, and therefore we can implement it to rule 26. According to rule 26, TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. R is the radius of this circle. Again, according to rule 26, chord TD intersects with chord BQ at 90 degrees at point C. Therefore, according to rule 26, TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36, plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225. So in total, if you found out that 25 plus 324 plus 36 plus 225 equals to 4R squared. 25 plus 225 is 215, 324 plus 36 is 360. So in total, if you found out that 250 plus 360 equals to 4R squared. 250 plus 360 is 610, so 610 equals to 4R squared. We divided this equation by 4 and found out that R squared equals to 152.5. Our task is to find out the area of this circle. The area of any circle is equal to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is R squared. So the area of our circle must be equal to pi R squared. But R squared is 152.5, so we substitute R squared by 152.5, and finally found out that the area of our circle must be equal to either 152.5 pi square units in its size, so in terms of numbers, the area of our circle must be equal to 479.09 square units in its size. So in both methods, we arrive to the same result. Okay, thank you very much.